Hello, everybody, officially. Welcome back to Intro Physics, day 19. We are going to continue our talk on energy, and let's just get right to it. I'm going to go ahead and share my screen. All right, can you all see the questions, Kat?
Yes.
Yes.
Great. Okay. So yesterday we had been doing some example problems on energy, and we ended with this example of an Atwood's machine, right? This was kind of our advanced example that went through when we have friction in our system as well, not just potential energy that we're considering and kinetic energy, but also this energy or this work done by friction that kind of takes energy out of the system. So this was our advanced example because it had friction involved and because it had two objects in our system instead of just one. So this is where we left off yesterday. And now, starting off today, I would like for you guys to think through a couple of questions about this roller coaster. So we have a roller coaster here. We're going to assume the cart starts at 2 meters per second. So up there at the top, it's moving 2 meters per second to the right. And what I want you to do, or attempt to do, is to put the locations, the points A through E, in order from lowest speed to highest speed. Okay, so take a couple of seconds, think through that, and then we'll talk through the answer together. All right, so you can base your answer on past experience if you've ever been on a roller coaster sort of like this before, or you can base it off of your understanding of energy. Both are valid, but our correct answer here is B. So the cart is going to be moving the slowest where it has the least amount of kinetic energy. And according to conservation of energy, where it has the least kinetic energy is where it has the most potential energy, right? Because if the total amount of energy is conserved throughout the whole roller coaster, then those two energies kind of transfer between each other, right? So slowest moving means lowest kinetic energy, which means highest potential energy. And if we know our equations for potential energy, we know we have a higher potential energy when we're at a higher height above our reference level or above the ground. So the place where we're the highest is A, and then D, and then B, and then C, and then E. Okay. You may have also felt this too if you've been on a roller coaster. Right before you go down the hill, you're moving pretty slow, right? And so again, when you're about to go down the hill, you're moving fairly slow. So A and then D, those are both peaks of a hill. B is sort of the peak of a hill. It's the top of the loop, right? And then you know that as you're moving down the loop, you're speeding up. You get faster and faster. Okay. So related question then, put the locations in order of lowest potential energy to highest potential energy. Now that we've answered the first question, this one should be pretty simple to answer, right? Think about what it means for potential energy. We'll notice that we have the lowest potential energy when we're lowest to the ground, right? And the higher you get, so from E to C to B to D to A, the higher you get, the higher your gravitational potential energy is. And so if you notice from the first question to this question, our answers are exactly reversed from each other, right? So lowest to highest kinetic energy and lowest to highest potential energy, those two answers are reverses of each other. Again, because of conservation of energy, right? If we have a high potential energy, that means we have a low kinetic energy. If we have a low kinetic energy, that means we have a high potential energy. They are inversely related. Okay, so now let's do some actual calculations based on this roller coaster. We're still going to assume that it's starting at 2 meters per second there at point A. Now we get the additional information of the mass of the cart, 350 kilograms. And I want to know how fast it's moving at each point. And I want to know the normal force at point B. Okay, so here are some equations that I wrote down because we haven't gone through rotational motion yet, but we might have time to touch on it next week. So here are the equations that may be unfamiliar to you unless you've taken physics in high school. But the centripetal force is mass times the centripetal acceleration. Okay, so when we're dealing with circular motion, centripetal, I'm going to emphasize it that way, centripetal force kind of pulls you into the center, whereas centrifugal force makes you kind of flee away from the center. So it feels like it's pushing you out from the center. That's actually an imaginary force. Centrifugal force is not a real force. It's a perceived force that's actually due to inertia, right? The tendency of your body to want to keep doing what it's already doing. Centripetal force is a real force, though. That's the force that holds you in. And so on our roller coaster, since we're not like flying out of the top of the loop, there's something holding us in, and that's the roller coaster rails, that normal force kind of supporting the roller coaster cart on the rails. So that's a centripetal force directed towards the center of the circle. Okay. And so our centripetal acceleration is the velocity squared divided by the radius of the circle. All right, so let's take a look at the speed at each point. We already know the speed at A, that was given to us as 2 meters per second. At D, that's our next fastest, right? So I'm going to go in order of slowest to fastest, just like we did in the previous questions. So at point D, we want to know what the speed is. We know some things about point D. We know how high it is above the ground. And we know how high point A was above the ground, right? Point A, or that initial height, is 25 meters. Point D is this 12 meters plus 4 meters, so that's 16 meters above the ground. Okay, so in this example, since I didn't give you any way to calculate friction, we're going to assume that friction is negligible, that it doesn't exist. And so the change in energy due to other or outside forces is 0. We're not considering air resistance, we're not considering friction, nothing like that. Okay, so our change in energy due to those things is 0, which means our initial energy equals our final energy, conservation of energy. So our initial energy is made up of kinetic energy plus gravitational potential energy, and likewise our final energy is made up of kinetic plus gravitational potential energy. So here we have those written out, just like we did in the example problems yesterday. Kinetic energy is 1/2 mv squared. Potential energy is mgy or mgh, depending on what variable you use for height. And now if we plug in what we know, in this case, I didn't just cancel out the masses, which you are absolutely welcome to do, but just for the sake of showing you an example where we include the mass in the calculation, I just left it in there. So 1/2 times mass times speed squared plus mass times g times the height initially at point A equals 1/2 times mass, we don't know this speed, plus the mass times g times that final height. Okay, so lots of numbers to plug into your calculator, but when you do the math and go through that simplification, you'll see that you get a final speed at point D of 13.4 meters per second. Okay, so that's our speed at point B. Now B is our next highest position. right? That's at a height of 12 meters. So I'm still going to use A as my initial point, just because we know for sure that our numbers are correct for point A. If you were unsure whether or not you were right in your calculation for point D, then you can just use point A as your initial throughout the whole problem, right? So again, initial height at point A is 25 meters. Our final height at point B is 12 meters. We go through the same setup that we did before. So I wrote it out exactly the same way that I did when we were solving for point D. Right, we're still not concerned with friction or air resistance. So we're conserving our energy, which consists of kinetic and potential. And now the only difference here is that we're plugging in a different number for our final height. Everything else stayed the same. Okay, so this whole left side of the equation is the same as it was when we were solving for point D. And again, the only different number here is the height, the final height. So that gives us a final speed of 16.1 meters per second. Okay, now let's just take a quick second, ask ourselves, do these answers make sense so far? Okay, from our conceptual questions at the beginning of this example, we should remember the order of like slowest speed to fastest speed as being A, D, B, C, E. And that's what we're seeing in the numbers too, right? A is slower than D, which is slower than B. And there's a bigger height difference between A and D than there is between D and B. So there's a greater difference in speed between those points than there is between D and B. Okay. So now we know our speed at B. We're looking for our speed at C. Our point C is at a height of 3 meters above the ground. And again, if I still use point A as my initial height, then nothing changes in my setup of the problem except for that final height, which has become 3 now. So our speed at point C is 20.9 meters per second, which is faster than point B, 16.1. So that checks out. And now finally, our speed at E. Point E is right at ground level, so it has a final height of 0. Okay, nothing else changed in our setup of the problem except for that final height of 0. And so we get a final speed at point E of 22.2 meters per second. Okay. Questions about that part so far?
Were we supposed to go through that on our own or
Go through the math on
just
your own?
together? Yeah.
Yeah, you're welcome to. I have it all written out for you, but if you would like to check my work with your own calculator, you are definitely welcome to do that. But like I said, since I'm using point A as my initial point for each of those, like speed at D, speed at B, C, E, all of those use A as my initial. That means that none of these numbers on the left side of the equation changed at all. And the only number that changed is the very last one that corresponds to the final height that we're looking at that point of interest. So once you've calculated the left side of the equation, it doesn't change and the calculation should go a lot faster. Ayana, you are raising your hand.
Can you walk us through like how you got from the last equation to the answer?
From here to here?
Yes.
Sure. So I think I actually have my calculator. I do. I have my real calculator today. Okay. So I'm just going to start typing into my calculator the numbers that I have here. Okay, so 1/2 or 0.5 times 350 times 2 squared. Okay, so that first term in our equation is 700. And then plus 350 times 9.8 times 25. I'm putting that in parentheses. Okay, so the left side of my equation, if I can read this backwards in my screen, is 86,450. Okay, that's the left side of the equation. The right side of the equation, here, let me go back. So, well, we can do it. Okay, it's fine. We can do it with 0. 350 times 9.8 times 0 is 0, right? So that term we don't really need to worry about for this calculation. Okay, so we just have that 1/2 times 350 times speed squared. Okay, so we know that 86,450 equals 1/2 times 350 times speed squared. So to get that final velocity or the final speed by itself, I'm going to do the opposite of whatever is being done to it. So since we're dividing it by 2 over here, I'm going to multiply both sides of the equation by 2. So 86,450 times 2, we'll get rid of the 1/2 on that side. And now that speed squared is multiplied by 350. So I'm going to divide both sides by 350. And that will take away that term. So now that we've done that, 494 equals speed squared. So if we take the square root of that answer, we get 22.2 meters per second.
Okay, I got it. Thank you.
Perfect. Okay, any other questions about this part? I did ask another question about the roller coaster, but any other questions about how we got the speeds? Okay, let's take a look at the normal force at point B. Okay, so we found that the speed at point B is 16.1 meters per second. And here I'm going to draw a free body diagram of the cart at that location, at point B. So we know we have the force of gravity pulling it down towards the center of the earth. And in this case, the normal force, the supporting force, is also down, right? Because the cart is kind of suspended underneath the rails. I'll do it this way. Here's the cart. It's suspended underneath the rails. And so the rails are actually pushing it down, right? Because as this cart goes around the loop, its tendency is going to want to be to fly out of the loop, right? If there were no like ceiling railing there, it just go woo and just keep flying up. But there is a railing up there. So that railing is pushing it back down around the loop. And if you've ever gone around a loop in a roller coaster, you feel that kind of push down as you reach the top of the loop. So that normal force, that supporting force, is pointed down as well in this case. So there's a question in the chat. In what other situations would the normal force act against the object? So go down. Let's say you throw a ball up in the air and it hits the ceiling. That ceiling would impart a force downward, right? Because the ball is traveling up, but the normal force, the ceiling's force, is going to be stopping that motion from continuing upward. It's going to be downward. Yeah, you're welcome. That's just another example that I could think of off the top of my head. Okay. And then we're not considering friction still. So these are the only two forces that we have. Like I said, we'll talk more about circular motion next week if we have a chance. But this is the equation that I had listed at the beginning of the problem that you can just trust me on. So our centripetal acceleration is the speed squared divided by the radius of the circle. Okay, so we found the speed at point B. The circle or the loop is 12 meters in diameter, which means the radius is 6 meters. So that speed squared divided by the radius is an acceleration of 43.2 meters per second squared. Okay, that's not our final answer because that's an acceleration, not a force. So we need to remember Newton's second law that tells us the net force equals the mass times the acceleration. So the net force in this case is the normal force plus the force of gravity, right? They're both in the same direction, net force plus the force of gravity. And that's going to equal mass times the acceleration. Yes.
So you would multiply the mass and acceleration to get the net force and just work from there.
Yep, that's right. So since we're interested in the normal force, I took this force of gravity and I moved it over to the other side of the equation by subtracting it. So the normal force equals mass times centripetal acceleration minus the force of gravity, which is mass times g. Okay. So when we plug in our numbers there, we get a normal force of 11,690 newtons. Okay. Questions, comments, concerns about example number 8? Okie dokie, let's move on. So I do want to spend a little bit of time today talking to you about springs, because springs also do work in systems, and we've been ignoring that up until now. I mean, I briefly mentioned it, was that Monday or Tuesday? But now we're going to actually look into it. So when we have springs, springs impart a force on the object. So the force from a spring is equal to negative kx, and this is called Hooke's law. You'll use this in several lab experiments in Physics 1 lab. So that k is called the spring constant. That basically tells us how stiff the spring is. So how easy it is to compress it or stretch it. And the unit of a spring constant is newtons per meter. So how much force it takes to compress it a certain distance, that's our spring constant. So if you've ever like taken apart a pen, like one of the clicky pens, and played with the spring, you'll notice that they're very easy to compress, because otherwise you wouldn't be able to just click it with your pen with your thumb. So those pen springs have a very low spring constant. They're very easy to compress. But your car shocks are much more difficult to compress, right? The weight of, they have to support the weight of your car. And obviously a pen spring is not going to be able to support the weight of your car. So those springs are much stiffer and would have a much higher spring constant. X in this equation is the displacement from equilibrium. So if you have played with springs before, you know that you can stretch them or compress them. Either one of those distances away from equilibrium is x. Okay, because if we stretch it, that's a distance away from equilibrium. And if we compress it, we're squishing it some distance as well. And that negative is important in this equation. It tells us that it's a restorative force, that regardless of whether you're stretching the spring or compressing the spring, it's going to want to go back to equilibrium. So we call that a restorative force. It wants to restore itself to equilibrium. So the force is opposite to the push or pull, right? It's desiring to do the opposite of whatever you're doing to it, right? If you're squishing it, it's desiring to spring back open. And if you're stretching it, it desires to spring back closed. Okay. So compressing or pulling a spring, compressing or stretching, takes more force the more you change the length of it. So the more you squish it together, the harder you have to push to squish it together. And vice versa, the more you stretch it, the stronger you have to pull the farther you stretch it. Right, so that's a restorative force. Okay, so let's think through Hooke's law here. We have a 3.5 kilogram weight hanging off a spring that's attached to the ceiling. The spring stretches 18 centimeters while it's holding the weight. What is the spring constant of this spring? Okay, for the sake of time, we're just going to go through this together. So here's a picture of what's happening, right? We have our spring, and this would be its equilibrium position. If there's nothing attached to it and it's just kind of chilling there, hanging from the ceiling, this is the equilibrium position. But now if we add a weight to the bottom of it, it's going to stretch out that spring some distance, delta x. So if we want to know what forces are acting on this weight here, we have the force of gravity pulling down, which is mass times g. Oops, wrong way. And we have the force of the spring holding up this weight as well. Okay, this spring is not bouncing up and down, it's just hanging. So we are free to use Newton's third law here and say that these two forces are equal and opposite to each other because we're maintaining an equilibrium situation here. It's just kind of, it's allowed to be at rest, is what I mean. So that means that this spring force pointing up is equal in magnitude and opposite in direction to the force of gravity that's pulling down. So the way we calculate the force of the spring is negative kx. The way we calculate force of gravity is mass times g. X, that displacement distance, is negative 18 centimeters because it's stretching it down. So negative 18 centimeters, which we want to use meters here because spring constant is measured in newtons per meter. So 18 centimeters is 0.18 meters. Okay. So we can plug in all of the things that we are given. We don't know what K is. That's what we're trying to find. So negative K X, that difference in the position, equals the mass times gravity. And so that gives us a spring constant value of 191 newtons per meter. Now, if you had left off this negative here in the displacement, then you would have gotten a negative value for your spring constant, but spring constants are always positive. So if you get a negative spring constant, that would be a good indication that you dropped a negative sign somewhere that you should have included it. So question in the chat, would there ever be a situation where the spring constant, okay, where X is positive? Yes, absolutely. There would be a situation where X can be positive, and we will look at some of those later on. Okay. So that's how we calculate force of springs, but springs also impart energy onto our system as well. So energy is stored if the spring is compressed or expanded, right? And if you've ever played with springs, you kind of just know that, right? If you compress it and then let go, it's going to quickly snap back to its position. Or if you stretch it and then let go, it'll snap back to its equilibrium position. So whenever a spring is stretched or compressed, it is storing energy that it will then use to move back into equilibrium. So that means it is a type of potential energy. Energy is being stored. It has the potential to be used later. Just like with gravitational potential energy, when we raise something up off of the ground, it has the potential to fall then due to gravity later on. Right? So that's a potential or a stored energy. There are a lot of different ways that you might see spring energy written out as a variable. So potential energy of a spring, PESP, not very common. This one is fairly common, U sub S for potential energy Remember, U means potential energy due to a spring. Or USP, same idea, but usually I see it written as US. SE means spring energy. I haven't really seen that one frequently at all. Or U elastic, that's the second most common one that I've seen. So either US or UEL, those are the two most common ways I see it written. The units of that are joules because it's a kind of energy. And the energy in a spring is calculated thusly as 1/2 kx squared. Now this equation is very, very similar to your equation for kinetic energy, which is 1/2 mv squared. So maybe that's a good memorization help for remembering these equations. Maybe it makes it confusing because they're written very similarly. Hopefully it's more helpful than it is confusing. But energy in a spring is 1/2 kx squared. 1/2 times the spring constant times that displacement from equilibrium squared. Okay. Put a box around it because it's important. All right, so here is an example using spring energy. A spring in a physics lab launcher has a spring constant of 12 newtons per meter. It is compressed 0.09 meters and used to fire a 20-gram ball. How fast is the ball going at the moment of launch? Okay, so first thing that we need to notice is that our units for the mass of the ball are no bueno, right? We want kilograms, not grams, because if the spring constant is in newtons, newtons, remember, has kilograms kind of embedded in it, kilogram meter per second squared. So we need our mass to be in kilograms. We need our distances to be in meters.
You would have to divide the 20 by 1,000 to get into kilograms.
That is correct, right? So here's a picture of what's happening. Okay, we have this launcher, and it's going to compress and launch a ball up into the air. So in this case, we're not concerned with air resistance or friction, so that other work is 0, right? There's nothing going to be taking energy out of our system. This time we do have a spring that we're concerned with. So we do need to remember this equation for spring energy, 1/2 kx squared. But still, since we're not dealing with any type of energy or any work that's taking energy out of the system, we still have energy being conserved. So our final energy equals our initial energy. So at the beginning, all the energy is spring potential energy, right? So when this is compressed, all of that energy is being stored in the spring. It is not yet moving, so there's no kinetic energy. At the end, though, once the spring has decompressed and has launched this ball up into the air, now all of that energy is kinetic because the spring is no longer compressed. Okay, so our equation here, 1/2 mv squared is 1/2 kx squared. Conservation of energy tells us that those two things are equal to each other. So I didn't bother writing like initial kinetic energy versus final kinetic energy and initial spring energy versus final spring energy, because again, at the beginning, kinetic energy is 0, so that factors out of our equation. And at the end, spring energy is 0, so that final spring energy factors out of our equation. We'll notice that we have a 1/2 in both sides of the equation, so we can cancel that out. So our mass here, which I converted to kilograms by dividing by 1,000, mass times speed squared equals our spring constant times that compression distance squared. When we go through and do that math, 12 times 0.09 squared divided by 0.02, and then take the square root of that answer, we get a speed of 2.2 meters per second. All right, so here's another example to think about. Still using a launcher with a spring as a spring constant. So this spring constant is 17 newtons per meter. We're going to compress it this time 0.12 meters and use a 25-gram ball. So this time, instead of being interested in how fast it's going, I want to know how far up, how high does the ball go? Okay, so again, for the sake of time, we're just going to talk through this one together. But I do recommend that you work through it yourself later on as well, so you know how to do it. Okay, so our relevant equations here: spring energy 1/2 kx squared, kinetic energy 1/2 mv squared. And since this launcher is now going to be leaving the ball is going to be leaving that launcher platform and flying up into the air, we also need to consider the gravitational potential energy, mgh. I wrote it as mgh this time, just so you get used to seeing it written with a slightly different variable that your professor might use. Previously, remember, we've used mgy. Same idea. Okay, so here's the situation now. We have our launcher that was compressed and then allowed to decompress, and it launches the ball up into the air, straight up. So we don't know what that final height is, but we're going to call the initial height, our zero height, to be the height of the platform. Okay. So again, we're going to start by asking ourselves this question: are there any other or outside influences, outside forces that we have to consider, like friction? In this case, no, we are not considering friction or air resistance. So that work done by other things is zero. So energy is conserved. Initial energy equals final energy. So right here, when the ball is as high as it will go, it is momentarily stopped. The speed is momentarily zero as it changes direction from going up to going down. So at the maximum height, kinetic energy is zero because the speed is momentarily zero. So right there at that location, that final location, the only thing that we really need to be concerned with is the gravitational potential energy, right? If kinetic energy is zero at that location and the spring is no longer being compressed or stretched at that location, then we don't need to consider those forms of energy. Now, initially, remember when we had compressed this spring before we allowed it to launch, kinetic energy was zero there as well because it had not yet started moving. And gravitational potential energy is zero because the ball has not yet left our reference point of the platform. So the only energy that we have initially is that spring energy when it is compressed. Kinetic energy will be non-zero in between these 2 points, but we're not concerned with that for this point, for this problem, right? We're just concerned with initial and final, not the midpoint. So we really don't need to consider kinetic energy at all for this problem. So that means that 1/2 kx squared equals mg final height. Plugging in what we know from the problem, 1/2 k, our spring constant, is 17 newtons per meter. That distance that it is compressed is 0.12 meters, and that will be squared. The mass of the ball, again, we don't want it to be in grams, we want kilograms. So we take 25 grams, and divide it by 1,000 to get to kilograms. G is 9.8 meters per second squared, and that final height is what we're looking for. So when you type in your calculator, 1/2 times 17 times 0.12 squared divided by 0.025 divided by 9.8, you'll end up with a final height of 0.5 meters. Any questions about example 11? Okay,
No.
cool, thank you. Example 12, we'll just keep doing some problems together. You'll get the hang of them the more examples you do, the more practice you do. You'll start seeing the patterns. So here's example 12. A block, a ramp, and a spring. Oh my. All right. Let's do it. A 7.8 kilogram block starts from rest and slides down a rough incline. Okay, hold it right there. What is the key word? Actually, two keywords in that sentence that we need to pull out and look at.
Rough.
Rough. What's the other one?
Incline.
True. Not the one I was looking for.
Starts from rest.
Rest. Yes. Rest and rough. Those are the two keywords that we need to look at. Because remember, from rest tells us about the initial speed of the block, which is 0. And the fact that it's sliding down a rough incline tells us that we are dealing with friction. Okay. The friction experienced by this block is equal to 15 newtons. The block starts off 3 meters above the ground and slides 5 meters down this rough ramp until getting to a frictionless plane. Okay, so now this tells us we only have friction during that section of the ramp, the incline, and no friction once it leaves that ramp. Okay, that's an important distinction. This plane, the frictionless plane, is 4 meters long. The block then hits a spring compressing it. The spring constant is 9,100 newtons per meter. How much is the spring compressed? All right, so looking at this problem, it seems a little bit intimidating. It seems like there's just so much happening in this problem. And that is why you will often see this type of problem on a quiz or test or homework. Because it really just tests whether or not you can read and comprehend what the problem statement says. So always draw a picture. Okay, draw a picture. So I'm going to label our picture now. Okay, so I'm putting this bottom frictionless plane as my reference height of 0, which means that this block starts off at a height above that of 3 meters. The length of the ramp is 5 meters. And we are dealing with friction, right? It's explicitly stated in the problem. The friction experienced by this block is equal to 15 newtons. So we do have other work that we need to consider, and that is due to friction. So thinking back to our lessons from earlier this week, the work done by friction is force of friction times the displacement times the cosine of the angle between the force and the displacement. That does not mean the angle of the ramp. That means the angle between the force of friction and the displacement. So if the displacement is down the ramp, remember, friction is always opposing motion. So friction points up the ramp. And those two, regardless of the angle of the ramp, those two things, the force and the displacement, are exactly opposite each other. Okay, so that's an angle of 180 degrees. Okay, so our change in energy here, final energy minus initial energy, equals the work done by friction. Okay, so let's think about our forms of energy here. Excuse me. So at the end of this block's journey, we know it is compressing this spring. So we know we're dealing with spring energy at the end. But at the end, the block is sitting on that level floor, which is our reference height of 0. So there's no gravitational potential energy to consider. And if we want to know how much it is compressed, like its maximum compression, that will happen when it stops moving. right? It's compress it as much as it can and it will stop moving. So our kinetic energy at the end is 0. That's why the only form of energy we have as final energy is the spring energy. Okay. Initially, the block is starting from rest, so our initial kinetic energy is 0. There is no spring being compressed or stretched at the beginning, so our initial spring energy is 0. But the block is a height above our reference plane of 3 meters, so there is a gravitational potential energy to consider initially. Okay, so that's why we only have these terms as our energies. This one is our final energy, and this one is our initial energy. And that equals the force of friction, which we were told was 15 newtons, times the displacement over which friction acts of 5 meters, times the cosine of the angle between them. Remember, there's no friction down here. So friction is only doing work on the system for the portion that there is friction. And that's 5 meters. Okay, so our spring energy is 1/2 kx squared. Our gravitational potential energy is mgy. And 15 times 5 times the cosine of 180 degrees is negative 75 joules. Okay, so plugging in our numbers, we know our spring constant is 9,100 newtons per meter. We don't know how much the spring is compressed, so we're looking for X. We know the mass of the block is 7.8 kilograms. We know G is 9.8 meters per second squared. We know the height initially is 3 meters. Okay, so when we go through and we solve this in our calculator, right, we would do 7.8 times 9.8 times 3. And then since that's being subtracted over here, we would add that to the other side of the equation. So negative 75 plus 7.8 times 9.8 times 3. Multiply both sides by 2 to get rid of this fraction 1/2. And then divide that by 9,100. And finally, take the square root to get our answer for X to be 0.184 meters. Whew. All right, so reading through this problem, it seemed like it was going to be incredibly complicated. But I hope that you found it maybe wasn't as complicated as you thought from reading the problem. And hopefully you saw that drawing a picture does indeed help. Any questions about this one?
How did you get the potential energy of the spring as your final? That second line there after energy final minus energy initial. Yeah.
This one.
How did can you explain that
Yeah.
portion?
Yes. Okay. So the final is not just like at the bottom of the ramp. The final is like the ending position of the block. So we know that this block slides down the ramp and then slides across the floor into the spring and compresses the spring. And that's its final position, is compressing the spring. So since this block is sliding into the spring and compressing it, that means that spring, as it's compressed, is storing energy. And then it's going to want to like shoot back out into its equilibrium position if we allow it to do so. So the fact that this spring is compressed means that it has potential energy, spring potential energy. Okay. But at that location, the block is resting on the level floor, which is our reference height of 0. So there's no gravitational potential energy. And the block, once it's compressed the spring as much as it can, will either stop moving or will change direction as the spring like stretches back out. We don't know what happens afterwards, but we don't need to. At that location of maximum compression, the block is momentarily stopped. So the kinetic energy is 0 at that location. And that's why we only have the spring energy as our final energy. There's no gravitational potential energy and there's no kinetic energy once this block has compressed the spring. Okay. Initially, when the block is up here on the ramp, we do not have kinetic energy again, because the problem tells us it starts from rest. So initially this block has a speed of 0. So it has a kinetic energy of 0. When the block is up here on the ramp, the spring is not being stretched or compressed. So it is not storing any energy at the moment. So the spring potential energy, when the block is at its initial position, is 0 as well. So initially, the only energy that this block has is due to the fact that it is a height of 3 meters above our reference point of the floor. So it only has gravitational potential energy initially. Does that make sense?
You, I guess I didn't get that we were that we were measuring it when the spring was fully compressed and the block just stopped. So
Yeah,
I
that's
guess I
true.
just
It
didn't make
doesn't-
that connection.
It doesn't explicitly state that in the problem, that like this is maximum compression or the block stops moving or something. That is a good point. That, I guess, is an assumption that I made if we want to know how much the spring gets compressed from this amount of energy that it has at the beginning. So from the gravitational potential energy itself at the beginning, how much can that compress the spring? And that would mean that all of this energy, except for the energy that's taken away by friction, all of that energy becomes spring potential energy, and we would figure out how much is compressed that way. Yeah, so that's basically what we did in the problem. Okay. Any other questions about this example?
No, I'm good.
Okie dokie. We'll pick up here tomorrow by just kind of summing up our conversation about conservative forces. And then I believe we'll have maybe a few more, not tomorrow, Monday. We'll have a few more final problems to sort of wrap up our thoughts. I have some chapter 6 and 7 like review questions, which would be the type of questions that you would see on a test. So I have those at the end of this PowerPoint as well. We can go through them on Monday if you would like to, or I can just post those questions and the answers on Canvas so that you can go through them yourselves. I'm fine either way, whatever we decide to do. But we'll finish up our talk about energy on Monday, and then we'll move into momentum. So I hope you guys have a great rest of your day, and I will see you Monday. Bye.
Thank you very much. Have a great day.
Have a nice weekend.
Thank you, Professor.
You too.